Hello, I'm Mr. Ho, and today I'll be giving a lesson on application of vectors. So first off, forces as vectors. Forces can also be represented by vectors that cause a change to an object that's either in a state of rest or in uniform motion. Like all vectors, it is made up of a magnitude and a direction. When there are two or more forces acting on the same object at the same time, there are two main concepts that can be discussed. The first one is resultant, which is a resultant force, and it's a single force that represents the sum of all the forces acting on the object. The second one is a composition of forces, or force composition, which points to the individual forces that make up the resultant. These individual forces are considered the components. Next, I'll be talking about equilibrium. So the equilibrium is a single force that, when applied, will keep the object in a state of equilibrium, preventing any further motion caused by the existing forces. The equilibrium is always opposite to the resultant. So, for example, let's say I have a force represented by this arrow, and it's called F1, and I have another force represented by another arrow called F2. So the resultant of these forces will be F3, or we can just call it F1 plus F2. So the equilibrium of these forces will look something like this, which is the opposite, or negative F1 plus F2, which is the resultant. So vectors in equilibrium can come in two forms. So the first one is non-collinear. And a non-collinear vector in equilibrium would look something like this. Let's say this is one vector. We'll call it A. This is another vector. We'll call it vector B. And this will be the third vector, vector C. So these vectors are three non-collinear forces that are in equilibrium, because A plus B plus C equals 0. So a vector in a collinear vector, or three collinear forces that make up equilibrium, can look something like this, where there's a vector, we'll call it A, and there are two vectors like this. They're in the opposite direction with the same magnitude, and we'll call it B and C. And if you're on top of each other, it'll still be A plus B plus C equals 0. So these are examples of a non-collinear vector and the collinear vectors that are in equilibrium. And an additional rule states that the sum of two of the vectors with the smaller magnitude has to be greater or equal to the third vector. So, for example, let's say A is maybe 6, magnitude 6, and B is magnitude of 7, while C has the magnitude of 3. This will be in equilibrium because the sum of 3 and 6 is 9, which is greater than 7. Okay, so let's move on to some example questions concerning these type of vectors, or application of these type of vectors. So example 1, a 15 kg block lies on a smooth ramp that's inclined at 10 degrees to the ground. What is the force parallel to the inclined plane needed to prevent the block from slipping? So first off, it's always good to draw a vector diagram. So we'll draw that now. We'll draw a ramp. So it's something like this. So this is our ramp, and let's say there's a box or something, the block is here. And we'll draw a triangle to represent the forces. So it says there's a 15 kg block, so the force would be 15 times 9.8, which is the force of gravity, and this in kg. So the force overall would be 147 newtons. So first off, we'll draw a triangle in a different color, like that, and then like that. Okay, so this would be a right angle. Oh yeah, sorry, forgot to draw the angle here. It's supposed to be 10 degrees. So if the angle is 10 degrees over here, then this angle would be 90 minus 10, which is 80 degrees. And here will be 82, and here will be 10 degrees. And 147 would be here, which is the force coming down. So in order to find the force that is parallel to the inclined plane, which is like that, we'll call it, say, vector F. It will be vector F equals to 147 cos 80 degrees, because if you look at this triangle right here, I'll use red. If you look at this triangle right here, this side is actually the hypotenuse, and this is a right angle. So we can use SOHCAHTOA, and using this angle right here, it will be cos, because it's adjacent to find this, and this is the hypotenuse here. So overall equation would be 147 cos 80 degrees. So if we calculate this, the force will be equal to roughly 25.53 newtons. Okay, so let's move on to the second example. A mass of 30 kg is suspended from a ceiling by two lengths of rope that make angles of 25 degrees and 30 degrees to the ceiling. Determine the tension in each of the ropes. So I've already drawn a diagram, simple one, showing how this would look. But let's convert this diagram into another diagram where we can actually do the calculations. So we're basically converting it into a new diagram where we're bringing this triangle on top. So how will we draw this? First off, we'll draw the same vector we drew, T1, but then we'll draw another vector, which is in this case representing T2, which goes like that. And then again, we'll draw the weight, or the mass of the 30 kg. And now we'll have an actual diagram like this. We can draw a line here. So it's 25 degrees here, and since we're just moving this over here on top, this would be 30 degrees. And if this is a right angle, up here would be 60, and here 65. We have so much information now. And this will be labeled T1, this is T2. As for the mass, again, we have to times it to get the force. So 30 times 9.8 equals to 294 newtons. So this would be 294. Now that we have this much information, all we need to do is a simple sine law, using 60 degrees for T1 and 65 degrees for T2. So sine 60 degrees over magnitude of T1 equals sine 65 degrees over magnitude of T2 equals, this is the known one, we have the magnitude here and the force angle here. So sine, and adding together 30 and 25, we get 55 degrees over 294. So basically, T1 equals to 294 sine 60 degrees over sine 55 degrees. Put this in the calculator, we get around 310.82 newtons. As for T2, almost the same, 294 sine 65 degrees this time over sine 55 degrees. This answer would be around 325.28 newtons, and you're done. So now example 3, now we have a question regarding application of vectors and navigation. So a jet plane is heading due south with an airspeed of 600 km per hour. So once you read that, you should start drawing your diagram of the airplane heading south. And it's 600 km per hour. And it's blown off course by a wind 50 km per hour from southeast. So since it's from southeast, you know two things. One, that's going from the southeast, so it's blowing towards around northwest, and the angle would be 45 degrees. So this 50 km per hour, and angle is 45 degrees here. So it wants you to determine the resultant of the ground velocity. So the ground velocity would be the resultant of the wind and the plane. And it would look something like this. And maybe we'll label this resultant. So, how would you do this question? Well, we have a lot of information. We have two side lengths and one angle. So obviously, we need to do a cosine law. So r squared equals 50 squared plus 600 squared minus 250 600 cos 45 degrees, which is the angle between, and then equals around 32003.6. I have to square root that. So all in all, equals 565.75 km per hour. So we know the magnitude of r, which is 565.75 km per hour. But now, to determine the resultant ground velocity, we also need direction. So we have a side length of this side, and we have the angle of this. So we can easily find the angle here to find the direction. So sine law, you can use cosine law too, but I prefer sine law. So sine 45 over r, which is 565.75, equals to sine theta we're finding is here by the way, over 50, because this is the opposing side length. So sine theta equals to 50 sine 45 degrees over 565.75. So sine theta equals to roughly 0.0625. Theta will equal to 3.58 degrees. And since this is the direction you're finding, your answer would be 565.75 km per hour. And the direction is south, 3.58 degrees west. So moving on to the final question. Chris can paddle a boat at 5 meters per second in still water. He heads out across a 300-meter river at an angle of 35 degrees upstream. He reaches the other bank of the river 400 meters downstream from the direct opposite point from where he started. So what is the current speed of the river? So First, as always, draw a diagram. It will help you greatly once you can visualize what you're actually doing. And this is my river. So it says that the river is 300 meters wide. So let's make it 300 meters wide. And it heads up at an angle of 35 degrees upstream. So, for example, if this is directly perpendicular to where he started from, let's say he started from here, A, he's going to head up 35 degrees upstream. So it goes up here, and the angle is 35 degrees upstream. And it says that he can paddle 5 meters per second. So this is his velocity. And we don't know the current, which is downstream. The current should be going here. But then he ends up 400 meters downstream. So let's show that he ends up 400 meters downstream. 400 meters. So his final destination from where he started will be here. So this is the information we know. Time to piece together the question. So first off, we want to find this angle right here. And we can find that. We have 300 meters, which is the horizontal component, and we have the vertical component, which is 400 meters. So right off the bat, we can do tan theta equals to 400 over 300. So it's SOHCAHTOA. So tan theta equals to around 1.33, and theta is 53.13. So theta is 53.13. So now we want to find this angle. We call it A. And since we know that this is 90 degrees here, we can find A by minusing it from 180 degrees. So subtract 90 degrees, which is this angle right here, and subtract theta, which is 53.13 degrees. So A is around 36.87 degrees. Why we need A? Because opposite here as an angle, you know sine law. So you can do sine law. Sine 36.87, which is the one we found, over 5 equals to, we want to find this whole thing, which is the current, the speed of the current. And what's opposite of this? Yes, the theta is here. The theta and the angle, 35 degrees. So this will be sine theta plus 35, which is around 88.13 degrees, over, it's a current, we'll just call it magnitude of W. So current speed equals to 5 sine 88.13 degrees over sine 36.87 degrees. Therefore, we can calculate that equals to 8.33 meters per second. Done. Well, I hope you learned something with this lesson, and good luck with calculus.